So we are going to finish this chapter today, okay? And we're going to get into, you know, the core of stoichiometry, like the real stuff. You know, last class we did some calculations, but, you know, today we're going to see what stoichiometry really is. Almost all of today should be review, okay? So I'm not going to go over balancing equations, guys. You know how to balance equations. I just want to make sure that you know that you cannot do a stoichiometry problem unless you are looking at a balanced equation. And let me say that if you come across some sort of chemical reaction, whether it's a multiple choice question, free response, it's in the homework, wherever, if you see coefficients already written in, you may assume that it is properly balanced, okay? You're never going to come across a situation where there are coefficients written in, but it's only like partially balanced and we're trying to like see if you notice. Haha, no. Okay, we're not doing that. If you see an equation and you don't see coefficients written in, you should assume that it is not balanced and check it. Okay? What's on this slide, guys, is sort of my way of visualizing any kind of stoichiometry problem. Okay? It's like my flow chart. And if it's not helpful to you, fine. If it is, great. Okay? But it doesn't matter what kind of stoichiometry problem you're dealing with. You will always have some sort of given information, and you will always be asked to solve for some kind of unknown. And probably I would say the most common stoichiometry situation is you're given some amount of reactant, and you're supposed to solve for an amount of product. But it doesn't have to be reactant to product, okay? It could be product to reactant, or reactant to reactant, or product to product. It can be between any two pieces of a reaction, okay? And you can be given any kind of units. You could be given a mass in grams, volume, number of atoms or molecules. The point being here, you have to convert to moles first of your given before you can get to your unknown. So let's just refresh our memories on how we do these conversions here. Okay? Tell me, guys, what is the conversion factor to get back and forth between number of particles and moles? Good. Avogadro's number. Okay? How about down here? How do you get back and forth between grams and moles? Very good. The molar mass, and where do you get that? Periodic table. I'm going to abbreviate and call this the MM from the PT. Molar mass from the periodic table. This one is a little, you're not going to see this one quite as much, but liters to moles, do you remember the number? 22.4, okay. Now, there's a little caveat with this one. See if you remember, you are only permitted to use that number if what? Okay, if it's a gas, first of all. So I'm going to put a little asterisk here. And some of you said it, I'm glad you said it. If it's a gas at STP, do you remember what STP stands for? Standard temperature and pressure. Okay, we'll talk more about this 2 chapters from now, but if you see that you're dealing with a gas and it says we're at STP, you are permitted to use that number. Okay, I'm not going to copy it over, but you're going to use the same conversion factors on the other side as well. How do you go from moles of one part of your reaction to moles of another? What do you use to get back and forth? Yeah.
The ratio of the coefficients?
Yeah. Yeah. You look at your equation and use the ratio of your coefficients. We call that a molar ratio. And you're right, it comes from the coefficients. Okay? Hence, it must be balanced. Okay? So, if you are very comfortable with stoichiometry and you don't need something like this, fine. But this, I find this just helpful. Okay? It also, if you use this flowchart, it's also going to help you know how many steps this problem is. If you are given a number of atoms and asked to convert to grams of your unknown, I can use this to know that that is a 1, 2, 3 step problem. Okay, 3 conversions would be involved. Okay, so we're going to get some practice in here. Number 1 should be pretty straightforward. Number 2 is a little bit more challenging. All right, but let's set the scene here. All right, the first thing that jumps out at me in number 1 is I have been given a chemical reaction. What should you do right away? Balance it. Is it balanced? No. Okay, so let's fix that problem. Okay. Now let's read the problem. It says, how many grams of each reactant? So I'm just going to come in here and kind of put little question marks. Grams of each reactant are needed to produce 15 grams of iron from the following reaction. All right, so this is actually 2 calculations within one problem. And remember, I said you're given, it doesn't have to be a reactant, it can be between any 2 pieces. In this case, your given is a product. Grams of product to grams of your first reactant, that's one calculation, grams of your product to the other. Okay? That should be pretty straightforward, because that's definitely review. If you finish that one, try tackling the second one. It's a little bit more challenging. Okay? So I'll put up the answer for number 1. Okay, check your work, guys. There's number 1. That was just kind of a warm-up. All right, let's look at number 2, which is a little tricky. Okay, I'm gonna help you get started on this one. Some of you I know have already solved it, but let's just talk it out. Okay. Number 2 says a piece of aluminum foil, length, width, thickness. Okay, let's just stop there for a second. Think geometry. What can you get from those 3 pieces of information? Volume. And in what unit would that volume be in?
Centimeters cubed.
Very good. Centimeters cubed. Okay. So aluminum is dissolved in excess HCl, that's hydrochloric acid. How many grams of hydrogen gas are produced? And then you're given some information here about aluminum. Ladies and gentlemen, do you see a chemical reaction given to you? No. Do you need one? Yes. Okay. This is what you need to get used to. Very, very rarely am I going to, or the AP exam, are they going to give you the reaction? You're going to have to come up with it. Okay, so let's talk that out. All right, a piece of aluminum. How do you write aluminum by itself? Good, it's not a trick question. Okay, is reacted with HCl, all right. They tell us, here's the word produced, that this is one of my products. You have to figure out the other one. And let's go through that thought process. Think back to Chem 1. Just look at the reactants alone. what type of reaction is this? Single replacement, exactly. Okay? These two elements are going to switch places. Okay? When hydrogen is by itself, it's one of our diatomics, it's H2. Please tell me, not the formula, please tell me in words, what is my other product here? Yes, sir?
Aluminum chloride.
You got it, aluminum chloride. What's the formula for aluminum chloride? Very good. It's one of our ionic compounds. You need to think about charges. Is that balanced? No. Absolutely it is not. So let's balance it here. Okay. Now we can solve this problem. And I'm not going to tell you how to do it, but focus on the fact that this is my unknown. And your given is something about aluminum. Think about what we just talked about here. Look at the other piece of information. Work it out.
Honestly, maybe I would do the same thing.
Okay, let me say something before you look at your answer, which might be a little different, and you think, oh man, I did the whole problem wrong. Okay. Do some of you have your final answer as 3.09? Okay, here's why. I kept 2 decimals here. You don't have to. Remember last class I said it's okay to round to 1 decimal place, and if you do that, this rounds to just 27.0. If you use 27.0, you get 3.09, and that's fine, okay? You don't have to carry 2 decimals. I did, but you don't have to, okay? So, when we start taking tests in here, if your answer is a little bit different than mine, most of the time that's not a problem because I can see why your answer might be a little different. And guys, this is more AP level, okay? The reason I say that is it's not just straight stoichiometry. I didn't just give you this starting value. You had to solve it for it. And please get used to using density as one of your steps in a larger problem. Okay, in this case, we had the density, we solved for the volume, we could find the mass. Sometimes you're given the density and the mass, you need that to solve for volume. That's very common in an AP problem. Using density as one of the steps within a larger problem. Okay? All right. So what else could we use stoichiometry for? We could use it for a limiting reactant problem. All right? Let's make sure we remember what that means. Guys, if you have a chemical reaction, it doesn't matter what reaction it is. If you have 1 reactant, 2, 5, 50, it doesn't matter. There will always be some reactant that runs out first. And tell me, please, what happens to a reaction when one of your reactants runs out? It stops. Okay, it's done. So the reason it's called a limiting reactant is because it limits how much product will be formed. Okay, now, your test on Monday. If you come across a limiting reactant problem, there's not going to be like these big flashing lights going, whoa, whoa, hey, this is a limiting reactant problem. You need to be able to recognize it. Okay? You know you are dealing with a limiting reactant situation if you're not given just one piece of given information, okay, or one starting amount of your reactants. Maybe you're given masses of both of your reactants, and you're supposed to figure out how much product is made. How do you know which one to use? Well, we're going to talk about that. Okay? Now, I will tell you this. Depending on who your Chem 1 teacher was, there are basically two methods, actually three, but basically two methods of doing a limiting reactant problem. No method is better than one of the others, okay? However, I'm going to go over a certain method with you that I personally think is the most useful method in an AP situation. It may be how you learned it, it may not, okay? Please don't write this all down, okay? We're going to go through an example problem together. And as I said, if you don't like this method, that's totally fine. There is another way, all right? And we can look at that if we have some time. All right, so this is just a very simple limiting reactant problem. It says ammonia is produced by the following reaction. This is actually a very specific reaction. It has a name. It's called the Haber process. Okay. Now, you come across an equation, what should you immediately do? Balance it. Okay, good. Get in the habit. Okay. Then it says, what mass of ammonia can be produced from a mixture of 100 grams of nitrogen, 500 grams of hydrogen. Okay, immediately, they haven't even said the words limiting reactant yet, but I know it's a limiting reactant problem because I know how much of both of my reactants I have. All right, we'll come back to this later. What mass of product can be produced? Okay, fine. Well, let's look at this. All right, let's start with the nitrogen. All right, I was given 100 grams of nitrogen. Let's do a quick 3-step conversion to get from there to grams of ammonia. So let's just do that together here. If you got something, close to that, depending on if you kept one decimal place or two. Okay, but that's basically the answer. That is, I should say, that is one possible answer. The method that I like to use for a limiting reactant problem is I take both of my given pieces of information and do a calculation for each one of them. So let's do the same thing, except this time I'm going to use the other amount of reactant. So that's my second possible answer. Okay, well, how do you know which one is the right answer? Well, the one that is the right answer comes from whichever reactant is the limiting reactant. Okay, now they didn't tell us that, which one is the limiting, but think about what the word limit means. A limiting reactant limits how much product I can get. Which one do you think is the right answer? Why 122? You're right. Yeah, it's the smaller one. Okay. your smaller answer will be the correct answer. Which means, which reactant is my limiting reactant? Nitrogen. Okay? What do you call the other reactant? Your excess reactant. Good. Now, let me just say something it's going to seem kind of odd, but limiting reactant problems are fairly common on the AP exam. Okay? And here's the thing, you've got to be really careful about what is the problem actually asking you. This one in particular said, how much product can be made? So I put a box around the amount of product. But what if the problem said, which reactant is the limiting reactant? Show calculations to prove your answer. Well, I still have to show all of this, but if I put a box around this, I would lose a point. Because the question said, which reactant is limiting? It didn't say how much product can we get. That's a product. That's not a reactant. Don't put a box around it in that case. You'd come back and probably making a statement is the best thing. Nitrogen is the limiting reactant. Okay? Just be careful what they actually ask you for. Okay? So my preferred method for a limiting reactant is to do 2 calculations and to look at which one gives me the smaller answer. Let's come back to here. Okay. How much unreacted material remains? What they're really saying, let me say it to you in another way, how much excess reactant is left over? That's really what they're asking us here. So, first of all, which one was the excess reactant? Hydrogen. Okay. We had 500 grams. Since I know it's excess, I know that not all 500 grams will be used up. Okay. Let's come back here. If I started with 500, and I know there will be some left over, what I really need to find here is how much hydrogen was consumed. I want you to throw out some ideas. There's more than one way to do this. How could I solve for how much hydrogen was consumed? Absolutely. What she's saying is that 122 grams of ammonia, that is the amount of product that will be made. I know that. So I could start there and convert that back to grams of H2. See how much hydrogen was consumed. So let's do that, and then we'll talk about another way we could have done it. Okay. That's one way to find that number. What's another way that I could have done that? Correct. Yeah. So there's lots of ways to do it. What he said was start with your limiting reactant. I mean, we know that that's all going to get used up. Grams of nitrogen to grams of hydrogen. No matter what we do, guys, we're going to end up with the same number. And what do I do from here? Subtract, yeah. So I had 500 grams, 21.6 grams were consumed. So I get this. Okay. may be new to you, okay? This dealing with the excess reactant, that might be something you did not do in Chem 1. Maybe you did. Right? So we've seen some basic stoichiometry. We've done a limiting reactant situation. What else could you use stoichiometry for? Yield. All right, let's talk a little vocabulary. Theoretical yield, okay, really just means an amount of product, usually grams of product. And guys, think about what the word theoretical means. I mean, when you use that word in your everyday language, you know, usually you say something like, well, you know, theoretically we could do blah, blah, blah. Theoretically just means like, well, in a perfect world we could do, and that's what this means here too. It's the mass of product you would get if your reaction was perfect. 0% error. Do you think that's likely? No, it's not. Okay? There's always error. Now let me tell you something. Your theoretical yield, you will always have to calculate it. It will never be given to you. You will always use stoichiometry to find it. It's never going to be given to you. So there's theoretical yield, there's actual yield. You go into the lab, you run this reaction with some kind of error, because we just can't help that. The amount of product you actually get, that's your actual yield. Put the two together and you can calculate a percent yield. Actual divided by theoretical. A comes before T in the alphabet. And guys, just so you're aware, a percent yield is basically putting a number to how good a job you did in the lab. All right? On our next lab, I'm going to have you calculate a percent yield. If you get a percent yield of like 95%, I think you're doing a pretty good job. If you get a percent yield of like 34%, something went wrong. All right? And I will not do this, but if any of you, which many of you will, go on to take a chemistry lab of some kind in college, they are serious with this, okay? They will have you calculate percent yields, and if your labs are anything like the ones I took, if you get below a certain percentage, they will make you redo it. Okay, you're going to solve this. I'll set it up for you. Okay, I'm always trying to model that thought process of how to tackle a word problem. All right, it says aluminum burns in bromine, producing aluminum bromide. How nice, they gave us the products, or product. In a lab, 6 grams of aluminum reacts with excess bromine. Okay, do not let this word scare you. This is not a limiting reactant problem. In fact, they're making it easy for you by telling you that bromine is not the limiting reactant, so it must be aluminum. 50.3 grams of aluminum bromide are produced. Calculate the theoretical and percent yield. Do you see a chemical reaction given to you? Nope. Let's write it out. How do you write aluminum by itself? Al. Very good. How do you write bromine by itself? Good. Br2, one of our diatomics. Aluminum bromide? Very good. Balanced? Nope. Okay. All right, we're given 6 grams of aluminum, and remember, let's start here. Theoretical yield means grams of product. as I said, you're never going to be given the theoretical yield. You'll have to calculate that. So if that's the case, what's that? I mean, I have to always calculate my theoretical yield. What is this number? Yeah, that's your actual yield, which you will then need to get this guy. You take it from here. Yeah, good question. She asked, for the final answer down here, how many decimal places? I mean, technically speaking, by going with rules of sig figs, it should have 2. But if you, had 84.9 or 85.0, it's fine. Okay, so limiting reactant and all the all the types of yield are really just applications of stoichiometry. Stoichiometry is a tool we use for these other things. All right, are you ready for the last slide? You're going to love it. This is putting everything together. Okay? I'm not even going to set this one up for you. I want you to do it. All I want to call your attention to is the fact that I see things about percent yield in here. I also notice that I'm given amounts of both of my reactants, so what does that mean? It's also a limiting reactant problem. Enjoy. You'll love it. All right, so here's the deal. I'm going to put the answer up. If you're not ready, just don't look up. Okay? I know that's easier said than done, but if you're not ready to see the work and you want to try it for yourself, just don't look up. Hard. Here's the second part. And guys, as we said, remember there's more than one way to calculate how much of your excess reactant was consumed. This is just the way I chose. You may have gone a different way, and that's all right. But ladies and gentlemen, that is the end of chapter 3.